Hey everyone, welcome. Today we're going to jump right into C#, moving from the basic nuts and bolts of syntax all the way up to the kind of strategic thinking that really separates great software from just, well, code that runs. So, let's kick things off with a big question. What's the real difference between code that just gets the job done and code that's built to last for years? It's about so much more than just making the compiler happy. It's all about a thoughtful, robust design, and that's exactly what we're going to unpack.
All right, let's dive in with C#'s core building blocks. Every massive, complex application you've ever used, it's all built on a solid foundation of these fundamentals, so let's make sure we've got them down cold.
At the very bottom of it all, we have data types. They're the rules that define what kind of information a variable can even hold. And since C# is what we call a strongly typed language, you got to be specific. You can't just throw any old value into a variable. You have to declare its type from the get-go.
Now this slide points out an absolutely critical distinction in C#, value types versus reference types. The easiest way to think about it is this. The stack is like a super efficient, tidy stack of papers on your desk. Last in, first out. Simple stuff like integers, your value types, live here. The heap, on the other hand, is like a big open warehouse for larger, more complex things that need to hang around longer. Reference types don't store the big object on the stack. They just store a little address card that points to where the real data lives in the warehouse. And trust me, this isn't just academic nonsense. Understanding this is crucial for performance and avoiding some really nasty bugs.
So, to wrap that up, C# basically sorts its data into three main buckets. You've got your value types, like numbers and characters. Then you have reference types, like strings or any custom class you build. And then there's this third category, pointer data types, but that's for special, unsafe code, a whole other can of worms for another day.
Okay, so we've got our data stored. Now what? We need to actually do stuff with it to control how our program flows. And for any kind of repetitive task, our go-to tool is, of course, the loop.
Before we even touch a line of code, this little flowchart just nails the whole idea of a loop, right? You ask a question. If the answer is yes, you do something, and then you go back and ask again. If the answer is no, you break the cycle. Simple, but so powerful.
So, how does C# actually pull this off? Well, the classic for loop has a really clear four-step dance. First, you set up a counter. Second, you check if a condition is true. Third, if it is, you run your code. And fourth, you update the counter. Then you just repeat from step 2 until the condition is false.
And boom, here's what it looks like in actual code. This one little line, for int I equals 0. I is less than 5, I++, does all of that. It initializes I, it checks the condition I is less than 5, and it increments I after every single pass. It's elegant, efficient, and an absolute cornerstone of programming. All right, we've got data, we've got flow, but a big pile of variables and loops isn't a program, it's a mess. We need structure. We need to organize our code into logical, reusable pieces, and that's where classes and interfaces, the real blueprints of our code, come into play.
The absolute best way to think about a class? It's a blueprint. Simple as that. The blueprint for a house isn't a house, right? It just defines what a house has, like rooms and doors. When you actually build the house, you're creating an object or an instance from that blueprint.
Now, an interface, that's a little different. It's not a blueprint, it's more like a contract. It doesn't say how to do something, it just says that you must do it. An interface is a list of promises, guaranteeing that any class that signs the contract will have a certain set of abilities.
Okay, this table lays out the nitty-gritty differences, but let's cut to the chase. The huge difference is inheritance. A class can only inherit from one abstract class, but it can implement many interfaces. Think of it like this. A car is a vehicle. That's inheritance. But it also can be iDrivable, iLockable, and iRefuelable. Those are interfaces. Abstract classes define what something is, while interfaces define what it can do.
This whole idea of classes and interfaces naturally leads us to a much bigger, more strategic question. We know how to make the blueprints, but how should they relate to each other? Now we're moving up to a core design principle, choosing between inheritance and composition.
When you get right down to it, there are really two ways to connect your classes. You've got inheritance, which is an is-a relationship. It's rigid, like a family tree. A dog is an animal. Then you've got composition, which is a has-a relationship. This is way more flexible, like building with Legos. A car has an engine. So how do you decide? The golden rule is pretty simple, actually. Use inheritance when one thing truly is a specialized kind of another. But for almost everything else, you should lean towards composition. It gives you so much more flexibility. Think about it. You can swap the engine in a car, but you can't really change its parents, right? All right, for our last section, let's talk about something that is absolutely critical. This is what separates hobbyist code from production-ready software: mastering exception handling. Because let's be real, in the real world, things are going to go wrong.
And here's a really important mindset shift. The goal isn't just to stop your app from crashing. Honestly, sometimes a clean, predictable crash is way better than an app that keeps running with God knows what kind of corrupted data. Good exception handling is all about creating software that is reliable and, just as importantly, diagnosable.
So in C#, our main tool for this is the try, catch, finally block. You can think of it as a three-part safety plan. You try to run the risky code. If it fails, you catch the error and deal with it. And then, no matter what happens, the finally block runs, which is perfect for cleanup, like closing a file. Okay, now I need you to pay close attention to this next part, because it's a super common mistake I see all the time. Someone will catch an exception and then just rethrow it like this. It seems logical, but it has a massive hidden side effect. Why is this so bad? Because doing it this way destroys the evidence. The stack trace is like the crime scene report for your code. It tells you exactly where the problem started. When you throw E, you're basically wiping the original location clean and telling the system the fire started right there in your catch block, which is a lie. Now look at this. The fix is so simple, it's almost easy to miss. You just use the throw keyword all by itself. No variable next to it, just throw. And that is the right way to do it. Just using throw on its own keeps that original crime scene report intact. It tells the system, hey, I saw the problem, but I'm passing the full story up the chain. It's a tiny syntactical change that makes a world of difference when you're trying to debug a problem. And that really brings everything together, doesn't it? We've gone from the tiny building blocks of data all the way up to high-level strategy and error handling. Because getting your code to compile and run, that's just the starting line. The real question you should always be asking yourself is this: is my code reliable? Is it readable? And is it truly ready for whatever the future throws at it?